Welcome to Module 2 on development of the Connecticut DOT's ABC Decision Matrix. We're pleased to again welcome our speaker, Tim Fields, Connecticut State Bridge Engineer. Tim?
Okay. This Module 2 is about the development of our CTDOT ABC Decision Matrix. So this was developed over about a 3-year period. We didn't rush this, could have been done a lot quicker, from about 2014 to its release in 2017. It was developed as a collaborative process with major assistance with Mike Cuomo with CHA Associates. Mike's firm is one of our consultant liaison engineers that helps manage our bridge program, providing oversight to task-based consultants to help take some of the load off of our design teams here at CTDOT. So, Mike, with his background with ABC at this point in time, from a nationwide perspective, was going to be a good help. And he had just developed or worked with Utah DOT for development of a decision matrix, ABC decision matrix for them. Our group here was about 5 individuals, up to including our District 3, Construction District 3 engineer, Mark Rolfe, who is now our Deputy Commissioner of DOT, after having been our Chief Engineer here several years before that. So the matrix was used on a pilot basis for a few years while we were tweaking it. And also, just before we put this out, it did have some inputs from for user traffic impacts, and we consulted with our traffic engineering group, and they requested we do a bit more to help take the load off of them. So there would be tools within the matrix for bridge engineers to determine user impacts, traffic impacts on any given ABC alternative. I think key here, and I mentioned this before, is our goal is to have this matrix used in all projects, bridge projects involving deck replacement, bridge superstructure replacement, and entire bridge replacement. So benefits of ABC: improving site constructability, total project delivery time. This is huge with standalone bridge projects. And work zone safety for the traveling public. The shorter duration we're out there in bridge construction projects, the safer it is for workers on the job site. Overall, we found traffic impacts are reduced. There may be more extreme short-term traffic impacts with ABC, but overall, they're generally reduced. Certainly on-site construction time is reduced for standalone bridge projects. And weather-related time delays can be more easily mitigated. Implementation at CTDOT for ABC. We definitely understood the benefits of ABC. The 2 early projects Mike spoke about demonstrated that, and management understood that. There was still, I would say, there was a little bit of a lag going from, the success of those 2 early 1990s projects to where we are basically in early 2000. So we're early, if you know, we did those 2 early projects without the benefit of an ABC decision matrix and without attempting to verify cost increases associated with ABC. So one of the goals with the matrix was to try to obtain a better measure of cost, construction costs, both for the ABC elements in the project, construction costs that might be avoided with conventional construction with temporary bridges or temporary widening. And we're going to talk more about that in the next few slides here. In looking at the, during the development of the matrix, we looked at examples of work that was done elsewhere. Two prime examples were the Utah DOT matrix and the Oregon decision matrix, which were the Oregon very complex, the Utah more straightforward, easier to manage, and a model that we wanted to use, we decided to use and tailor to Connecticut ABC priorities. So that's what we did. We took a middle ground approach using, I'd say, the best here of what we found with the Utah DOT matrix. One of the feats was creating a weighted scoring logarithm, and we'll get into that very shortly here. Developing a simplified road user impact process. That actually took quite a while to come up with an analysis method that would take the load off our traffic engineering folks in determining user impacts for various ABC and conventional bridge construction alternatives. Also, comparing, it was important to compare ABC costs to conventional bridge costs, and most significantly, to try to put a dollar value on overhead cost reductions that can be achieved through accelerated bridge construction, a benefit for bridge construction if a project can complete a year early. So our approach to user costs was not to try to put a dollar value on users' impacts. This is the traveling public. We felt that it was not real money, and we didn't want to basically combine user impact. We'll say that those are not real dollars that we can spend or save compared to the real dollars that we can spend or save with the actual bridge design alternatives. So our user cost impact ratio, what you'll see here when I get into the spreadsheets, here is we're comparing ABC versus conventional bridge construction. Calculate the unit of measure for user impact as a person day. A person day would be the equivalent of an individual sitting still in traffic for 24 hours. Many of the user impacts are for seconds or minutes times the number of the ADT concentration on the bridge times the duration that we're out there. So to make it more easy to manage that, we are using a person day as a unit of measure here for comparing the total traffic impacts from one alternative to another. Real important in the matrix is trying to get a handle on the overhead cost in running a job, savings that might be achieved from a reduction in contract days for an ABC project versus a conventional project. This is real money, and actually sway a decision from a dollar value alone on whether ABC is actually cost savings on a job or break even or maybe slightly more expensive on a project. But it's real dollars that the department spends. If we can save a year on a job, that could amount to more than $500,000. The factors we use are $20,000 per month per engineer inspector out there, and the office rate ranges from $2,000 to $4,000 or $5,000 a month, depending on the size of the office required for the project. So other things that affect project cost that could make ABC more cost competitive here, or perhaps even save money, is signaling, temporary signals that may not be needed if you have a long-term one-way alternating setup, multiple stages of construction, elimination of temporary bridges or overbuilds. Very often, the public is willing to tolerate a much more severe impact to traffic for a very short time and for the benefit of having that job complete much more quickly than a conventional project. So our approach to cost analysis here, there's one sheet in the our decision matrix that is strictly on costs here. So the preliminary cost evaluation is done for ABC and conventional. In this case, this is a hypothetical bridge project with a cost of $2 million. There is no overbuild required for the conventional option here. For the estimated construction inspection though is $2,000 in this case for the monthly office cost, and then $40,000 a month for two engineers here that would be associated with the project for a net of $42,000. So the time savings in this hypothetical project here using ABC, and that's often very achievable for a small bridge over a river, or say even in the Seymour project to try to stage that conventionally in that situation probably would have doubled the size of the project in length. In this case here, this hypothetical example, 12 months here, our estimated premium for ABC in this hypothetical project, 20%, and that's not far off from some of our projects, SPMT projects. These cells down here are MPT savings with ABC, things that we might not need to put in an ABC project here. So in this case, we could have had overbuild for staging that was zero here, not included. This project did need a temporary bridge, but the conventional project would have had a $40,000 temporary signal that the ABC did not require. So, these cells show us MPT savings of $40,000 from construction costs alone. The cost analysis, the spreadsheet is actually comparing our total premium for ABC project. That comes from the 20% times the $2 million, $400,000 here. Our cost savings from ABC, $504,000. This comes from the 12 months of reduction in construction duration times the $42,000 here, plus our temporary signal that we don't need here. And that's actually temporary signal in this cell here. So our net cost for ABC is minus $144,000. What that tells us is the ABC is less expensive than the conventional construction. And the reason why is the 12 months associated with the savings in ABC times our monthly CE&I costs and office rental of $42,000. So in this screen alone, you see the ABC yielded a net savings in real dollars and cents. So there's a number of other ABC measures that get brought into through an algorithm into a scoring matrix. I'm just going to briefly discuss that. You'll see these weight factors times these variables yield an adjusted score. These weight factors for these 10 parameters are brought in to the spreadsheet here. They are calculated earlier by inputs that a designer will make. The weight factors are weights that we actually struggled with a bit and we experimented with a bit to come up with what we felt properly reflected the values and importance of each of these factors in making the proper ABC decision or not. And you'll see user impact reduction is very high at 30. Average daily traffic is very high. And cost analysis is very high at 30. These total 108 here, and these were normalized to 1 over 100 here in providing our adjusted scores in this column. Over here, In this section of the spreadsheet, we're looking at the idealized optimal ABC project where everything is a 5. A 1 to a 5 would be a range for 1 be not advantageous for ABC to a 5 highly advantageous to ABC. So the total ABC score for the particular project is divided by the total maximum score times 100 to yield an ABC rating. And that drops us down to this chart right now that provides correlation between the ABC rating and whether or not ABC would be a viable choice for the project. So, these weight factors are factors that might vary from state to state here. For us, our user impact was very important, so we had this as a very high number. This could perhaps even be made larger. But we felt comfortable with the 30 as a weight factor. So right now I'm going to discuss these 10 different measures here that went into the ABC decision. These are a matrix. These are factors here that a designer would insert here in the table here. 0, no traffic impact, to 5 being very high traffic impact. There's another sheet. This is the second sheet in the decision. Actually, this is part of the first sheet in the decision matrix. Compares user impact for ABC and conventional for traffic on the bridge and also traffic under the bridge. If there's traffic under the bridge, that would be impacted by bridge construction. So, average daily traffic is inserted here. Delay time is inserted in this cell. Construction impact inserted in this cell for conventional construction. Similar process is used for ABC construction. And then the same process for conventional construction for the roadway under the bridge, and for the ABC option, looking at traffic under the bridge. In this cell down here, we are looking, the spreadsheet actually computes total aggregate impact time for the ABC and for the person days. And a computation is made by the spreadsheet here and for user impact reduction. And a negative value would show that ABC actually has more impact than conventional construction. Not something that we typically find, but could. The equation here is 1 minus the ABC impact time divided by the conventional impact time. So if the project has from a 0 to 5 here a very low number, 1 to 20% reduction here for ABC. That one would be entered in here by the spreadsheet. The spreadsheet's actually capturing that, or up to 5 here if it's 81 to 100%. So weight factors. This is an example here of the results of the delay time computed for both conventional and ABC construction. This is our sample bridge, a short span bridge replacement bridge over a waterway. That means there's no roadway underneath to contend with. Precast integral substructure modular deck beam with detoured traffic is the ABC alternative. The conventional alternative is staged construction, 1-lane alternating. So the conventional is compared to the ABC from a net delay time. And it's expressed, as I said, in person days. That's the equivalent of 1 person sitting in traffic stationary for 24 hours. So, just looking at this, if our delay time is 3 minutes with our average vehicles per day times 7,000, then we're multiplying that times 300, and then dividing that by factors to provide us person days. Same thing done for the ABC alternative. So in this case, we had conventional impact 4,375 person days, and the total aggregate time for ABC 1,167 person days. Significant reduction for the ABC, 73% reduction with user impact. So bridge location, this is one of our 10 measures that we have here. Again, rating 0 to 5 here. 0 being very low benefit for ABC by this measure alone, up to 5 here for urban bridge and emergency services, where minimizing construction time would be of utmost importance. You'll see a weight factor of 5 divided by 108. You'll note we had the weight factor for user impacts and costs each at 30 divided by 108. So this is a much lower weight factor. Same for this, typical details. 1 for bridge, very complex, unfavorable geometry, maybe where every deck panel might be unique, with a flaring bridge. To 5, very simple bridge, well suited for simple geometry and typical standard details. Work zone geometry, a weight factor of 8 over 1.8. So we put a slightly higher premium on this. This is a measure related to the safety of workers and motorists. With the work zone that we have, for an example, with 1 lane alternating traffic, the potential for an accident is much greater for a project than one constructed with a detour that we might find with an ABC project. So projects that are short duration projects with good geometry and flow might be lower on the need for work zone geometry to be an important factor for consideration for ABC. Or 5, a long duration project with complex geometry and flow would be a very high candidate from this measure alone for ABC. Site conditions. So this is, this measures a function of what we're dealing with here, a constrained site, perhaps with significant right-of-way or limited or significant utilities or limited right-of-way space, buildings that may not be able to be acquired for situation of cranes necessary for the larger, heavier picks we might have, or potentially SBMTs or lateral moves that we might be looking at for an ABC. So this factor, we put a 5 over 108. Railroad impacts, are we near a railroad or not? If we're not near a railroad, it drops out of the equation here, so it doesn't skew our results. If we're over electrified railroad, we'd have a very high premium for ABC over versus, say, a freight siding here, where with extremely low traffic, where it almost becomes a non-factor. Again, the more time we spend over dealing with an electrified railroad or commuter railroad, the higher the benefit for an ABC approach. Cost analysis. So we discussed this earlier. This is the measure between ABC and conventional cost here. If we find through the spreadsheet computation that our ABC alternative is costing us up to 30% more, then we're going to put a 0 in here for a cost for ABC weight for cost. If we find, on the other hand, that we have a 5 down here, or that we have a cost reduction for ABC, then this becomes a 5. And then the variation between 0 and 30% spread out between these particular cost scores here that would be inserted in here, depending on what the cost factor, what your ABC versus conventional cost is. Then water handling here, if we're over water, we're not over water, it's a 0. If we are over water and we have significant limitations on work, time of year restrictions, that might push a job from 1 year to 2 years or 3, depending on the nature of the project. There can be a big advantage for accelerated bridge construction that might get us in and out in one season. Then waterway limitations here. Are we over commercial, over navigable water or not? So this is scored again appropriately here with these values we noted. And lastly, these values are brought, the various ratings of the various measures are brought into this table. And we discussed this briefly before. And this is the very same table you saw several slides earlier. This hypothetical project yielded an ABC rating of 75, meant it was a good candidate for ABC. We expect to come back and measure, evaluate these weight factors from time to time. We have not done that yet as a group to see if these should be reweighed to favor cost or user impact more or less, or some of these other measures that we have put in here. And this is an example of this 4-sheet spreadsheet as a whole. The user impact portion of this spreadsheet, Mike is going to discuss in much more detail in the following presentation, going through some supplementary spreadsheets we developed to be able to compute delay time for the ABC versus conventional alternatives. We talked about our cost table sheet here that compares ABC and conventional, and then the other 8 parameters are basically reflected in these cells here in the final ABC rating evaluation. Data is inserted in the yellow boxes, and the spreadsheet produces output in the white boxes. So as we discussed, the first cell up here is for the entry of description of the ABC project, what it is versus the conventional project. And we might be doing several of these for different ABC options on any given project. Again, we noted this cell computing traffic impacts, user impacts below and above the bridge. And then a note user impact reduction here for accelerated bridge construction. Sheet 2 is, we said, the cost evaluation sheet. We're looking at conventional cost versus ABC cost, putting premiums in here for accelerated bridge construction and recognizing the overhead costs with CE&I and office monthly costs in this cell here. And this, again, is a very important portion of the ABC analysis because, this could range from, $500,000 to $800,000 in a year, depending on the manpower necessary to staff the project and the size of the office needed for the project. And again, coming down here, final evaluation of net percentage of conventional cost of the ABC alternative investigated. And we went through some of these parameters here. These are the other ABC measures we discussed in more detail, showing now on the sheet 3 of the matrix. And sheet 4, these the ABC, the last of the ABC measures entered here, and then the spreadsheet computing the ABC rating for the particular ABC bridge alternative under consideration. We'll note again here for a bridge over water, these scores are 0 down here, so they don't skew the final analysis. Or the same thing if there's no environmental or water handling issues. If it's a bridge over a highway, this is also 0. Or if we're over a railroad, this drops out as a 0, so it doesn't skew the final denominator that's used in the ABC rating. So again, 60 to 100, good for ABC, 50, 60, marginal, and less than 50, ABC is probably not your first choice. So this was released, this matrix, after our pilot process here with a number of projects we used this on, and was released through an engineering bulletin in November of 2017. As I said before, we want its use on all deck replacement projects, superstructure replacement projects, and entire bridge replacement projects. It is a tool that's used during preliminary design, because a decision needs to be made at that point before we engage the public in our local town leaders, our town governments, on whether we're proposing an ABC project or not. Because the outcome of that dialogue becomes subject matter in our design approval document. So, I guess the last consideration is it's a tool, it's a management tool, and we have probably done ABC projects that didn't rate a 50, and we've probably done non-ABC projects on ones that were graded over 70 or so. So our management certainly has prerogative to choose to go ABC or not. I will note that the decisions that on ABC are at our division chief level here, and that's basically mid management here with the Department of Transportation. So I think that what that conveys is the confidence that our upper heads have in the decision making that we're all using here in evaluating ABC or conventional bridge construction alternatives for any given project. So that concludes this presentation.
Okay, thank you, Tim, for your informative presentation. We'll now begin the Q&A session. Paul?
Okay, Mary Lou, thank you, and thank you, Tim. We've got a few questions that came in mostly beforehand, but the first one was, what various levels of Connecticut's DOT were involved with the creation of the ABC decision matrix?
I think I noted that before. The task group included myself, Mike Cuomo, who was instrumental in helping us create this matrix and tune it to Connecticut DOT priorities. We had two other bridge engineers at that time. They were senior level engineers, and we had Mark Rolfe, who is now a deputy commissioner. At that time, he was a District 3 engineer, basically construction engineer in District 3. And he had actually coordinated our Q Bridge New Haven Corridor program, so very well versed in this area. So it was a fairly small team. Most important, though, is the involvement we had from traffic, because we were ready to come out with this matrix before we had these supplementary spreadsheets completed that were needed to objectify for bridge engineers, to provide a guide for bridge engineers on how to compute user impacts, because our traffic engineers said you can't go out with this matrix till you make sure you have the tools for your bridge engineers to do this work, so we don't end up having to do this work for them. So it did cause a little bit of a delay in getting the matrix out, but I think it's better for it because it now includes subjective measures for that kind of work. So I would say, that I would, include our, several engineers from our traffic division too, who were instrumental basically in making sure we had the right frameworks for that part of this analysis, because the user impact, as you see, is very highly weighted variable in the matrix. And we wanted to make sure we had an objective way to put a value on that, to how, so any two people could come in using the same data, come up with the same user impacts.
Okay, it's almost 20 after. I'm going to ask Ahmed if any questions have come in during the question and answers period.
Yeah, Paul, I do
Ahmed?
have one question. In the spreadsheet, do you directly account for accidents in the corridor? Does the number of accidents in the corridor influence the decision to use ABC?
Yeah, the answer is no. That's an interesting question, though.
Yeah.
Okay, that's all the questions we have, Mary Lou.
Okay. Well, thank you, Paul and Ahmed. We're at the end of the second 40-minute module. Thanks again to Tim for presenting the second module.